Welcome. This is our 20th video of the semester, and this one's going to depend wholly on the last one. We were looking for exponential solutions of different kinds, leading to what we call these characteristic polynomials. Solving these characteristic polynomials gives us different kinds of exponential solutions. But we haven't dealt with the case yet where we have some of the more interesting problems with what those the roots to the characteristic equation are. What happens if the two roots that we get are repeated? What happens if they're complex? These are the things that we have to deal with next. So we're going to do one case right now with repeated roots. So what happens if you get two roots and they're the same thing? What happens if you solve the characteristic equation and you find that they're both of the solutions? That can happen quite naturally. But in this case, it's different from the first case in that the discriminant, that's b squared minus 4ac, is equal to 0. That gives one repeated root, and that's this one right here. Minus b over 2a. You can just imagine taking the square root part of the quadratic formula, setting that equal to 0, and that's how you get it. But the problem is that it only gives us one solution. It gives us y1 equals e to the minus b over 2a times the independent variable, whatever that is. Now, we know from our theory that we need 2, and that there must be 2 in order to get the whole solution to a second-order linear homogeneous differential equation with constant coefficients. That has to be the case. So where the heck is the second one? We can't very well say that the solution is c1 times the first plus c2 times the first again, because then I could really have factored out the first and get a constant times that one. The 2 would be linearly dependent. I need 2 linearly independent solutions to get the general solution to a second order equation. But this is where something comes in really handy. The very first technique from this section, we did, I think, 2 videos ago, reduction of order, actually comes in really handy here. I didn't do this in our notes. I did it the first time I ever taught the course, I think. It's a little bit of a sloggy proof. It takes a little while. But it's great practice, and it's really cool to see how this extra solution comes up. So I very much encourage you to try it as a for you to try problem when you get the chance. It's in the for you to try section for that reason. And I've asked it on test before, so you should figure it out in case I decide to do that again. I don't know. Fair game, I guess. Regardless, if you use reduction of order, you find out that a second linearly independent solution is actually given by the same exponential, but this time times an x. So you get a general solution that involves e to the r1x, which is the first solution that we would have found, and then x e to the r1x right here. So this is the second linearly independent solution. This would be our y2. And this is our y1. You could factor it if you want to. I usually like to write each of them separately so I can see all of those different kinds of linearly independent solutions that make up the general solution. But as I said, give that derivation a try. It's very interesting and not super straightforward, so it's a bit challenging too. We're going to use that right away and try to find the general solution to this problem. So a constant coefficient, linear second order differential equation, and the characteristic equation for this one. Again, it's a polynomial in powers of r rather than derivatives of y. So it's 4r squared plus 12r plus 9 equals 0. And you might stare at this for a little bit and notice that it's a perfect square. You might use other factoring techniques like decomposition or whatever else, or factor theorem even, and figure out that you get the 2 repeated roots. This collapses down pretty quickly to 2r plus 3 all squared equals 0. And that means that r has to equal, well, what is it? Minus 3 over 2, it looks like, repeated twice. So in this case, right, you would go to write down your solution. It's as quick as ever, right? There's nothing super difficult about it. But, yeah, the general solution, you just have to remember the different form and write it down correspondingly. So we have y of t equals, it's c1 times e to the minus 3 halves t, and then plus c2. And then e to the minus 3 halves t, but then you're like, oh wait, repeated, it needs to be multiplied by an extra t, just like that. So we get a constant times an exponential, and then constant times t times an exponential. And that, in combination, will make up our general solution. So it's still just as fast, you just have to know what to look for. So that's one more case. We have one last one to touch on, and that is what happens when you get the two roots being a complex pair, which sounds like it might be very challenging. I'd say it probably is a little bit more challenging, but it's really not too bad. This, of course, arises in that last case, where the stuff under the root is less than 0, meaning you get imaginary roots. So the roots you get are going to have a real part, I'm calling it alpha here, and an imaginary part. And we'll call that beta. Of course, that I is the imaginary component. Think of it as the square root of -1. And believe it or not, despite having that an exponential solution that looks like it's complex, we can use some great mathematical tools to find a way to write this in terms of real valued solutions, which is kind of incredible. So if we just kind of blindly go forward and say, okay, well, it's e to the rx would be our solution, so it's going to be e to the power of whatever this r is right here, alpha plus or minus I beta. We can have two exponentials and write them down. Nothing else. E to the alpha plus I beta x, e to the alpha minus I beta x. Those are our two solutions. We can write them down. It's a little unsatisfying because, I mean, they're complex solutions. And especially if we're going to be using these to frame real world models and stuff, it would be really nice if we had a way of writing down real valued solutions associated with it. And in fact, there is a way to do that. So we're going to take this and we're going to use, as I said, some interesting math, really neat stuff in order to rewrite this in a way that's useful. So we are having here a complex solution if we just sub in those r's, but we're really just interested in real valued solutions to this course, or in this course, for our differential equations. How should we proceed? Well, Euler, not Euler. I mean, some people will say Euler, but they're wrong. This is one of those names that is pronounced differently from person to person, but the people that are right are the people that are saying Euler. So, you know, Euler just sounds like Ferris Bueller or something. Don't call it Euler, it's Euler. Anyway, Euler's formula is a really interesting formula in math, and it relates a complex exponential function to sine and cosine functions. This is something that you can prove even at a first year level using like Taylor's theorem, and it's not actually that bad to show. But it's a fascinating fact of mathematics that if you have e to the ix, this is the same as saying cos of x plus I times the sine of x. They're two of the same, right? What's on the left and the right are equivalent. And what we're going to do here is use this formula to rewrite our exponentials. So we had an e to the alpha plus I beta in the one. We had an e to the alpha minus I beta in the other, times an x in both the exponents. I'm going to use exponent rules and kind of break those up. This is e to the alpha x, e to the I beta x using exponent rules. Oops. And then, if I think about what this is, I have e to the I times thing equals cos of thing plus I times the sine of thing. I want to think of this for a second. There's an extra beta here, and you may not know what to do with that. The e to the alpha x, that's just, it looks like a real valued thing, so there's no problem there. We're just going to keep it there. This here is going to be e to the I times our thing here is going to be beta x, whatever it is. And we're going to get the following. As I said, e to the alpha x, that's just fine the way it is. E to the I beta x is going to be cos of beta x plus I times the sine of beta x. And if I do the same thing with e to the alpha minus I beta x, I can break that up in the same sort of way, but now I have a minus beta x right besides that I. And I'm going to get this, e to the alpha x cos of minus beta x. What do I want here? And then this will be plus I times the sine of minus beta x. Thinking of that formula. I'm going to be a little bit thoughtful about going forward. I'm going to be subbing both of these in, and it'd be nice to be able to relate the two together. And right now I have beta x's in one and minus beta x's in the other. But I can actually use some trig identities to match them up a little bit more carefully. You might remember the oddness, evenness identities, and I'm actually going to use these right here to make things a little bit better. So I'm going to put a little thought cloud up into the top corner because it looks like it's nice and empty up there. So you're daydreaming a little bit. I don't know about your daydreams. My daydreams don't usually involve this, but sometimes they do maybe. I'm going to say recall that if I have cos of minus beta x, it's the very same thing as cos of beta x, and that's because cos is an even function. What happens on one side happens exactly the same on the other. So what happens for negative x happens exactly for x. Cos of negative beta x is going to equal cos of beta x. I'm going to write here, cos is even. And we also have that sine of minus beta x is equal to, well, sine is odd. So what happens on one side happens oppositely on the other. So what happens for sine of beta x is going to be the opposite minus what happens on the other side, sine of minus beta x. So sine of beta x is equal to minus sine of minus beta x, or sine of minus beta x is minus the sine of beta x. And I'm going to use both of those and sub them in. So we're going to get here e to the alpha x, and then cos of minus beta x, and that's just the same as cos of beta x, and then I sine of minus beta x will be the same as minus I times the sine of beta x. So toss that around a little bit. It's kind of funny how some of these properties just come up surprisingly, but you just got to be ready for them. That's what we took all of those other math courses for. So, and sorry, that last one is because sine is odd. Out of context, sin is odd. I don't know. I guess we're all... Anyway, I'm just not going to go down the religious road there. Let's keep going. We're going to sub both of those expressions in. We have one for this first exponential. We have one for the other. And if I sub those into our formula for the solution that we had, we end up with, let's see, what do we have up here? It was y equals c1 times the first, c2 times the second. So we have y equals c1 times the first. Now, the first is that first bracketed term up there. It's e to the alpha x cos of beta x plus I times the sine of beta x. And then I'm going to have plus c2 e to the alpha x. And then it looks like we have a cos of beta x minus I times the sine of beta x. And this doesn't look like it helps at all, but what we're actually going to do is group the sine and cosine functions together. The exponentials look like they're fine. So I'll kind of keep those, I'll kind of factor those out front actually. I'm going to say, let's write e to the alpha x outside everything else. And then if I bring together the, let's see, the cosine functions, let's say, I'm going to get here in the first one, c1 cos of beta x. And in the second one, I have a c2 cos of beta x. So I have a c1 plus a c2 in front of the cos of beta x. So I'm doing kind of a massive bunch of factoring all at once, but you can get there in a couple of steps if need be. All I'm doing is seeing what's common to the cos of beta x's. And now let's do the sine. The sine is going to have here c1 times I in front of the firsts, and minus I times c2 in front of the second. So it looks like here we're going to get, let's see, plus. I'm going to write C1 minus C2, thinking of that minus sign right there, times the I in front of sine of beta x. Okay, check this out. C1 plus C2. If C1 and C2 are any constants, this is just a constant. And I have one, if you take a look, one function here, a cos beta x times e to the alpha x. That looks like it's totally real. Pretty cool. The second one is C1 minus C2 times I. I'm going to say that this is just a complex constant. But I want you to think back to our theory. We said that if you have one function that we know is a solution, in this case we have e to the alpha x times some, maybe complex number times the sine of beta x. But if we have one solution, any multiple of that is also a solution. And in fact, that includes complex multiples. It includes those multiples that are just real valued. So we can think of this as being some arbitrary constant in front of a sine function times an exponential. We actually get a second solution here that's e to the alpha x times sine of beta x. And that's what these are. There's one, there's the second, and we can take the general solution by a linear combination of the two. So if you get a complex pair, we need to be able to find the alpha and the beta, which are just the real and imaginary parts of that complex number that we get, which isn't actually that hard to find. We'll do an example, but we're going to get y of x equals e to the alpha x, so that's the real part right there. And I'm going to relabel my constants. I'm going to say C1 in front of a cos beta x and some C2 times sine of beta x. And all of this checks out with our theorems from earlier, I guess last week. This is a redefined C1s and C2s. Redefined C1 and C2, taken to be real. Again, thinking of that the theory of superposition, the ability to take any multiple of a solution and get back a solution. That's fine. This works really well, okay? And we have that the two linearly independent pieces involve exponentials times cos and exponentials times sine. The last thing I want to point out here is where these alpha and beta come from. I said it at the beginning, but it's important that I identify it right now. This here is the real part of the root r, and the beta is the imaginary part. The imaginary part of our, but we are going to assume that we take a positive value. So if you get like a plus or minus 2, you just take a 2 there. And you're kind of saved by the fact that you have the C1 and the C2 in front that would be able to adjust for that. So taken, we'll say that this is greater than 0. Okay, so we have these two different pieces, the real part, the imaginary part, and we can always get those from finding our roots. A little bit much, but hopefully you can look over this and make some sense of it. We're going to do a solution to an IVP here. So we have this equation, y double prime plus y prime plus 4y equals 0, with conditions of y of 0 equals 0, y prime of 0 equals 1. So we're going to dive in, find a characteristic equation. We'll get very used to this as a first step. As long as you have one of these linear higher order equations, that's what we'll do. And it's going to be r squared plus r plus 4 equals 0. I can't see a good way to factor that, so we'll use quadratic formula. Negative b plus or minus the square root of b squared minus 4 times a times c all over 2a. I think at the end we get minus 1/2 plus or minus, and then 1 minus 4 is negative 16 over 2. And you might want to rewrite this in terms of a, oh, that's not negative 16, it's 1 minus that. So my apologies, that should be a negative 15. So the way that we'll write this is minus 1/2 plus or minus root 15 over 2i. It's important to write it like that because using the language from the last page, minus 1/2 is going to be our alpha, and our beta is going to be the root 15 over 2. So those are going to be critical in figuring out what our solution is. Now, if you know what to expect, writing down that solution isn't bad. So I'll take this, go up, and we'll write down the general solution. It's going to be y of t equals, and then take e to the alpha, that's minus 1/2. T is my independent variable here. And then I need c1 cos of beta, root 15 over 2, t. Don't forget the t, because some students do forget that. And then plus c2 sine of root 15 over 2, t. Just like that. That's all there is to it, except we have an initial condition. So we have to apply the initial conditions now. So initial conditions. A little bit of work here because it looks quite grungy, we'll say. But let's apply y of 0 equals 0 first. So y of 0 equals 0. That's going to be subbing in 0 everywhere. I get minus 1/2 times 0. I get c1 times, well, it's going to be the cos of 0, right? So that's not bad. Cos of 0 plus c2 times the sine of 0. Using the initial conditions is usually pretty nice. This here is equal to just 1. Cos of 0 is just 1. Sine of 0 is just 0. So this is gone. And it looks like after all that, we're going to come down to this somewhat unsatisfying c1 equals 0. 0 equals c1. So that's kind of nice. We can honestly take that and sub it back in there before we take the derivative here, which is really great. We need to apply the second initial condition now. So we need so now we can apply the other initial condition, and that was, let's see, y prime of 0 equals 1. So y prime of 0 equals 1. I'm going to say, note, we found c1 equals 0, so we can ignore this term. But it's not wrong to take the whole derivative of the general solution and work with that. But we know that that first term is going to be dead anyway. In this original equation, it's basically not there. So why don't we keep things simple and work with that. So I need the derivative though. I have y prime of 0 equals 1. I need to find y prime of t before I do anything. And unfortunately, we have a product rule. Even if c1 is 0, I still have that the exponentials times a c2 times sine of stuff. So I need the derivative of the first, minus 1/2 e to the minus 1/2 t, times the second, c2 sine of root 15 over 2t, and then plus the first, e to the minus 1/2 t, times the derivative of the second, and it's a little bit awkward, I get cos of root 15 over 2t, and then the derivative of root 15 over 2t gives us an additional root 15 over 2 out front, just like that. Oh, and I forgot my c2, didn't I? So I need a c2 in there as well. I'll just write it right there. That should be fine. Okay, so double check to make sure this is okay, especially in that second one that I... So derivative of the first times the second plus the first times the derivative of the second is root 15 over 2. It comes out as a chain rule, cos of this, and I didn't forget my c2. So we're good. Okay, y prime of 0 equals 1, and we'll go right across and fill this in. So that's minus 1/2 e to the 0. We get a c2 times, well, a 0 here because I'm putting in sine of 0, maybe I'll just write down sine of 0. And over here I get e to the 0. I get this awkward root 15 over 2. I get cos of 0, which will just be 1. And c2 I'm trying to find. Again, sine of 0 is 0, so that's gone. This is 1. This is 1, and so is this. So it looks like this whole first term is gone, and I'm going to get c2 equals 2 over root 15. Just from doing a little bit of rearranging there. So c2 equals, 2 over the square root of 15. So I have my two different coefficients, arbitrary constants there. I've now figured out that what they are and pinned them down. I'm just going to add one piece so I can put in a final answer here. But the process is similar, right? We're still finding a general solution. We're still finding the constants at the end. Here, though, we have two initial conditions. You have to apply both of them. So therefore, the solution to our initial value problem is, well, it's the same thing as before. We take our y of t and we sub in the constants we know. E to the minus half t, c1 was nothing up there, and c2 is 2 over root 15. So I think we're going to get, if I'll write the constant first, 2 over root 15 e to the minus half t. And finally, the term that survived was the sine term. So sine of root 15 over 2t. Just like that. And this is exactly the solution that will fit our differential equation with those two initial conditions. So it's a little bit involved, especially when you have to do an initial value problem. You have a couple of conditions that are working there. And we've seen a couple of interesting cases today. The repeated case as well as the complex case. All three of them, repeated, complex, and the real ones we did in the last video, are really important. You need to be able to just know the form of those when you write down the solutions to the characteristic equation. But the flow is exactly the same. Solve that characteristic equation. Depending on what the kinds of r's are that you get different forms of a solution, and then you put them together at the end. If you have an IVP, then go and calculate your constants, and you should be good to go. Yeah, we have one more video when it comes to homogeneous techniques. The next one's going to be all about extending this to even higher order than second. So I hope you'll join me for that. It's not really too much harder, especially if this stuff is feeling pretty good so far. So I will see you in that next lecture. Take care for now.